Welcome everyone to ELPC Thinks. I'm Howard Lerner. I'm the Executive Director of the Environmental Law and Policy Center. And as you know, ELPC Thinks is where we bring together experts, political leaders, environmental leaders, and community partners to talk about new strategies for protecting the Great Lakes, the wild and natural places of the Midwest, and accelerating climate change solutions that can make a difference for our planet. Quick heads up. We're recording this ELPC Thinks on Facebook so we can share it with people who weren't able to join us today. And today, excuse me, we're going to be talking about the Great Lakes, the current state of Great Lakes water levels, where we are, what's likely to be happening, and our preparedness levels. In 2020, we had record flooding across our Great Lakes that impacted infrastructure, shorelines, communities, people's homes, businesses, public health, and where we live, work, and play. The past year was a little different. Water levels in Lake Michigan, Lake Huron plummeted, and we're now on track to be a little bit above average this summer, as I think we're going to hear from Drew Gronewold. Doesn't mean we're out of the woods. The impacts of climate change continue to affect the Great Lakes. Dr. Drew Gronewold is joining us again this year. Drew is an associate professor at the School of Environment and Sustainability at my alma mater, the University of Michigan. And Drew will talk about what the current state is of Great Lakes water levels, what those water levels mean for the future of the Great Lakes. He's an expert in hydrogeological modeling, works with the Army Corps of Engineers and NOAA on Great Lakes modeling and water levels and forecasting. We're going to hear about what's happening from Drew, and we'll have some times for Q&A and discussion. So please put your questions in the chat box, and welcome to Drew Gronewold.
Thanks, Howard. Thanks for that introduction. And just as a quick check, Howard, can you hear me okay? And can you see my shared screen okay?
Yes, I can. It's working great, Drew.
All right, great. Well, thanks everybody for taking the time on this, at least here in the Midwest, beautiful day. As Howard mentioned, my name is Drew Gronewold, and I'm based here at the School for Environment and Sustainability at the University of Michigan. And there's sort of four things I want to cover today in just the next 15 minutes or so before we have time for questions and answers. Just give you a little bit of an introduction to first some thanks, and also to some big picture backdrop that I'd like to offer for the discussion today on water levels. I want to take a look back to last year at where we were in May of 2021, and then talk a little bit about where we are right now, how we got here in terms of water levels, and where we're expected to go into the future. So to begin with, I would need to start out by giving some acknowledgments and thanks, because none of what you see today would at all be possible without colleagues, students, and other collaborators, many of whom work in federal agencies, including those on this screen, the folks I used to work with at NOAA, the National Oceanic and Atmospheric Administration, as well as the current crop of students, postdoctorate fellows, master's students, and undergraduates. Again, the work that I'm showing you today simply would not be possible if we didn't have this strong team. And we're also very thankful for generous funding from various entities, including the Army Corps, United States Geological Survey, Great Lakes Protection Fund, the Michigan Department of Transportation, and also the Council of Great Lakes Governors and Premiers. So with that, I want to provide a few introductory notes here. The first is that it's always important to remember when we talk about water levels, many people ask me, well, how should we learn? What should we do in terms of thinking about the future? And I tend to note that we have one of the longest continuous records of measurement of any large freshwater system in the world. So what I'm showing you on this screen is just to set the context for the discussion, the overall long-term history of Great Lakes water levels. If you look down at the bottom axis here, you can see we're starting with water levels going back to 1860. That's when gauges were first placed on all of the Great Lakes, all the way up to present. And then I have all four sort of lake systems on here, from Lake Superior all the way down through Michigan, Huron, Erie, and down to Ontario. And just for reference, on the left-hand side, we see water surface elevation here in meters. The red line that you see for each lake is the long-term average. The dark blue dot is the annual average, and the light blue is the monthly average. Now, we could spend a lot of time looking at all the different patterns here. We're not going to do that today, but again, the take-home messages here is we have an extraordinary long-term water level record for understanding historical dynamics. And today I'm going to be focusing a little bit more on Lake Michigan, Lake Huron, and the present. Now, another contextual point I want to make reflects a discussion that many of us are having here regionally, and it focuses on the ideas of water scarcity and water abundance on basin-wide scales, on continental scales, and on global scales. As Howard mentioned several years ago, there were folks in the Great Lakes Basin who were literally begging to have water diverted at above average rates out of the Great Lakes Basin in violation of binational laws. You see a woman on the right-hand side here begging to former Governor Cuomo to let more water out of Lake Ontario during extreme flooding conditions, which ultimately would have exacerbated flooding in Montreal, as we can see on the left in one of the New York Times articles from that time. But what I want to point out here is that we are now living in a basin where we have periods of water abundance and water scarcity, and we're getting conflicting messages about what to do or how to manage that water. Put differently, at this time period, when people were begging to have water dispatched from the Great Lakes Basin, there were other communities in the Great Lakes Basin or just on the edge of it that were running out of water and asking for water to be diverted as well. So two different means, one group trying to get rid of excess water and another group needing water either due to water quality or water quantity problems. This is an article from the Chicago Tribune in February of 2021, indicating that a lot of the groundwater aquifers below Chicago, and in this case, in the city of Joliet, are running dry. So one of the things that we are doing research on right now is trying to understand not just long-term water level variability in light of climate change, we're also trying to understand what external stresses on the Great Lakes might come in form of climate migration and extra basin demands for water that might stress our understanding of the water level dynamic. So with that context, let's take a look back to where we were in May of 2021. And here's a very simple image of water levels. I'm showing a much more condensed view than the one I did earlier. We're looking here basically from around the late 1990s up until May of 2021. The top panel shows Lake Superior water levels, just for context, and then this bottom panel are Lake Michigan and Lake Huron water levels. The blue dots are the monthly average water levels in each month during that time period, and the red line is the long-term average. So if you look back to where this record ends, I deliberately stopped it right at May of 2021 during where our last update was. And if you remember, the discussion of that time period had to do with record high water levels. And with the mouse click here, I'll add to the panel here what the monthly water level records were at that time. And that's this thin blue line that you see right here. So in other words, you can see both Lake Superior and Lake Michigan Huron coming extremely close to the all-time record high set back in the mid 1800s, 1980s, but also setting several new monthly records for the months leading up to October. So that was the context for May of 2021. And as part of that, we were looking at the science behind that water level rise. And what I had shown was this sort of extreme discrepancy between the amount of water coming into the Great Lakes Basin and then this abrupt decline in overlake evaporation. So in the top panel here, you see these processes on the land surface over time in the Great Lakes. These colored bars represent either above average or below average anomalies. So for example, in this panel right here, we see precipitation over the lake surfaces. And what this slide is intending to represent is that in the period leading up to those record highs, we had a profound, consistent period of above average evaporation, precipitation. And in the bottom panel here, we're looking at processes over the lakes themselves. So again, the top panels on the land, bottom panels on the lakes. And the idea here is that when we get to the bottom right, the net amount of water over all of the Great Lakes during that time period from around 2014 to 2020 was extraordinary. It was one of the wettest decades in recorded history over the Great Lakes. And we put a lot of that in context in a paper we wrote at that time, if you're interested, called A Tug of War Within the Hydrologic Cycle of a Continental Freshwater Basin. And the idea is this: nearly every climate projection for the Great Lakes indicates that things are going to get wetter and warmer in the long term. And what that means from a water levels perspective is that precipitation is likely to go up on average, but so is evaporation. And we try to think of those or conceptualize those as two competing forces on the hydrologic cycle. Precipitation causing water levels to go up, evaporation causing water levels to go down. And sometimes those forces offset and sometimes they don't. And we like to think of that as this sort of long-term tug of war. So let's take a look at where we are now and a little bit of how we got here. So let me go back to this slide. Again, I've stopped this slide deliberately at May of 2021. As Howard mentioned, we had just started to see some sort of decline, but we didn't know exactly where we were going to go at that point. And I can add in the following year. So here's where we were, and then this next set of blue dots that I just added with a mouse click shows where we are, a pretty profound decline in water levels since our update last spring. To put that into context, what I'm showing on the left over here for Lake Superior and Lake Michigan Huron is a yellow box. And what I've done here is I've deliberately drawn a box here that starts sort of around where water levels were at a peak in the late 1990s and where they went over time horizontally and down in water levels to where they troughed over a 2.5-year time period. So again, this is sort of to put into perspective the rate at which water levels were declining on Lake Superior in the late 1990s, and then the rate at which they had begun to decline from a peak in Lake Michigan Huron in the late 1990s. And if I take those two yellow squares and I superimpose them here onto the last peak on Lake Superior, Michigan Huron in recent history, this is what we see. So again, what I've taken these two squares from the left and I've superimposed them over here. And what we can see is that the rate of water level decline that we've experienced on Lake Michigan and Lake Superior over the past 1.5 or 2.5 years is almost identical to the rapid rate of decline that we saw in the late 1990s that set the stage for this sort of below average water level period during the late 1990s and 2000s. So where do we think we might be headed looking into the future? Well, from a long-term water level perspective, we've been synthesizing research for a couple of decades now. And a lot of that research can be shown in this slide here, where we're looking on the top panel at Lake Michigan Huron water levels in the past. So these blue dots are the historical water levels on Lake Michigan Huron. And then these bars and boxes and lines represent the range of water level forecasts from a variety of different studies going out into the future. And the take-home message from studies like this one is that there isn't a clear indication that water levels are profoundly likely to go up or down over long time periods, but rather we might be more concerned by interannual variability. And we just published a brand new paper that underscores this point in the journal Frontiers in Water, where we ran some more scenarios and we believe that the long-term average is just probably not likely to change as these two offsetting forces of precipitation and evaporation balance each other out over multi-decadal periods. But as I like to quote this paper that was published in the journal BAMS, the Bulletin of American Meteorological Societies several years ago, by a water management practitioner in New York State saying, 2100 doesn't keep me up at night. The things that keep the Water Management Distribution Authority and other practitioners up at night are things like week-to-week forecast or monthly forecast. So let's take a look at where we're headed over the next few months. And to provide context for that, I want to go back to actually May of 2020. This is the forecast that was made for Lake Michigan and Lake Huron back in this was March of 2020. And what we see here on the bottom axis here is time. We have these dashes that are the record highs. The black line represents what water levels actually were, and then the black dots right here are the average water levels. We have meters on the left and feet on the right. So each one of these lines that you see corresponds to what would happen to water levels if we had precipitation and evaporation dynamics comparable to a historical year. So the green line for here represents what would happen if we had precipitation and evaporation similar to 2019 all over again. And water levels would have shattered all-time records if that had happened. The gray band is what I want to focus on. It represents the full range of all plausible outcomes in light of historical variability. So that was the forecast that was made in March 2020. I'm going to add a red dot to the screen. That's where water levels ended up in the following spring of 2021. So we took a journey here from this point in the forecast. Water levels went up a little bit, and then they ended up here in the spring of 2021. If I advance to the next slide, we now look at what actually happened with water levels over 20 and 21. There's where we ended up Now let's go back to last year in May of 2021, same thing. Here was the range of all of the forecasts, and here's what ended up happening. So water levels declined, but still within the range of plausible outcomes. And here's where we are today. So if I jump ahead one more slide, here is April 2021 up till present, May of 2022, and looking out into the future. So the reason I just went through that exercise, if I take away this red dot, here are the current projections for water levels, indicating that it is very likely that water levels on Michigan Huron are going to stay above average. There's a slight possibility they might go below, but again, this gray band represents the full range of all plausible outcomes. And hopefully what I just walked through gives you some idea of what we might expect in terms of the range of variability within this set of outcomes. One final point I want to make with projections is that when it comes to these seasonal outlooks, I've mentioned this before and I want to underscore it again. In order to make predictions about water levels at any time range beyond 10 to 14 days, you need to have very accurate outlooks for the air masses that come across North America. These air masses on the screen here, the maritime polar air, maritime tropical air masses, and even the continental and Arctic polar air masses dictate the changes in temperature and moisture that come into the Great Lakes region. And until we have more accurate forecasts of how these air masses are going to move at timescales ranging from 2 months to 9 months and even out 1 to 2 years, until those become more accurate, it's going to be very hard to narrow down that range of uncertainty in the water level forecast over the same timescale. So with that, I want to end and thank everybody at the Environmental Law and Policy Center for the invitation to talk today and for hosting this seminar series, and also to thank a lot of the partners and sponsors who we work with on this topic and who help make foundational federal data available. So with that, I'll end, and I'm looking forward to discussion and answering questions. So Howard, thanks again.
You're welcome, and thank you, Drew. I was about to say, thank you for the good news, but I'm not so sure it's good news. It's important news, and it has, as we all recognize, implications both pro and con, depending on where you are and depending on what you're looking for in terms of changing water levels. Your graphs do a very good job of showing the notable changes in the past few years, and that some of the projections, if you will, are all over the map. What's your assessment on what models have been most accurate in previous years' predictions, and how do you evaluate the different types of projections? Can you give us a little insight into that?
Absolutely, Howard. So just to back up a little bit for context for the audience, there are a variety of models that are used to look at the climate of the Great Lakes and ultimately water levels of the Great Lakes. Some of them are based on what we call a combination of GCMs, general or global circulation models. These are continental and global scale models that then have to be scaled down to a region, in our case, the Great Lakes region, using another model called a regional climate model. So a lot of the forecasts that we get come from this coupling between GCMs and RCMs. There are dozens, if not hundreds of combinations of GCMs and RCMs that could be used for the Great Lakes. And there have been quite a few studies that have looked retrospectively at which models have done well over time. And my general assessment, Howard, is that there is no particular model that has consistently done extremely well over time. They all have flaws and they all have time periods where they have maybe above average skill, but the same models will have periods where they have below average skill. Another approach that I want to mention, though, aside from these what we call physically based models that are trying to reproduce the physics of the atmosphere and of the lakes, there are also statistical models. And our group is leaning a little bit more heavily in the direction of statistical models right now, because they allow us to look at what we call plausible scenarios and see how those manifest into water levels. But in short answer, Howard, there is no single set of models that we know of in terms of these GCMs and RCMs that have an above average level of skill. And we've tested that by looking at many different models over time, retrospectively. But again, no single model stands out as having better or worse skill than any other.
Drew, we have a lot of questions and comments, as I'm sure you anticipated. I'm going to try to combine some of them together. First
Sure.
of all, David Hales, Emily Mersel, all compliment you. Excellent presentation. I could go through the half a dozen comments and say, great job. So thank you.
Sure.
Couple of questions about longer term water levels. And I gather from what you're saying, we're less interested in the average. What's more important is the extremes at both ends, because that really affects the shoreline infrastructure, communities, the built environment. Are we looking at much more extremes, or are we seeing it gravitate to a middle point?
Great question. Well, I can, the answer is a little bit complicated, but I can answer the second part of the question first. We are not seeing gravitation towards a central point at all. In fact, if we look at water levels over the past, and let me pull up my water level plot here without taking too much time. So can you see the long-term water level plot there, Howard?
Yes.
So you can see at no point in history, really, especially on Michigan Huron, have we sort of hovered around the mean. But certainly over the past 20 years, what we've seen is a tendency to be away from the mean. And what I want to point out here is this period from 1998 through 2013, where water levels were actually remarkably stable, but very below average. And most everyone on this call probably remembers that. And what I think is important about it, that is right after we hit the record low in January of 2013 on Lake Michigan Huron, water levels embarked on a record-setting surge. And you may look and say, oh, there were other surges, Drew, in the historical record. We tested it and we found that this was the highest rate of water level rise during this period from 2013 to 2016. And then water levels have stayed up at a high level after that time period. So we think that the time period from 1998 till now, where water levels were low for a long time period, dominated by evaporation, and then this swing to above average water levels dominated by above average precipitation and a slowdown of evaporation, is most likely more indicative of the future than some sort of stability where those two forces just average each other out over time.
Drew, can you talk a little bit about the weather? What's the impact on water levels of rising temperatures, which would increase evaporation, as you were discussing, increased rainfall and severe storms, which would put more water into the system? How do water levels relate to that sort of temperature and other extreme weather events? Or are those just contrary trends? And as you sort of commented earlier, some of them offset each other.
Yeah, what a great question. So a lot in there in terms of fluxes in moisture and weather. Let me start with part of the question, which had to do with temperature. So when we are looking at the water balance of the lakes and we're trying to understand patterns of precipitation and patterns of evaporation, one of the things we often look towards is the fall, and how evaporation in every fall cycle is either above or below average. It turns out that most of the water level declines on the Great Lakes occur in the fall, and it's because that's when evaporation picks up. That's when cold, dry air goes across the lakes and waters are still cooling down. And this slide, I think, underscores part of what we look at, Howard, when we think about this. So what we're looking at here is a slide that the Army Corps of Engineers put together showing surface water temperatures across each of the lakes since 1995, I believe. And what you can see are all these gray lines showing every single May through May temperature cycle. And if you look at 2021 and 2022, this raises an eyebrow because it shows that, at least for Lake Superior, Michigan, Huron, or really for all the lakes, this fall time period was one of the warmest we have in this record. And what that suggests is when we have warm surface water temperatures during periods when cold air starts to move across the lakes, that's going to exacerbate evaporation. And that's pretty much what we saw over the past year. In terms of precipitation and weather patterns, the thing that we're looking at right now, and I mentioned this last year, is trying to understand where additional moisture comes from. And if we go back, I'm not going to take the time to go back to the slide of the air masses, but there's a lot of work being done right now to try to understand, believe it or not, individual storm tracks. and try to understand whether some of the big storms are bringing moisture, say, from the Gulf of Mexico or circling around from the Atlantic Ocean. Those individual storm tracks are really what we're looking at in terms of the accumulation of precipitation over time that might lead to increases in water levels. So there's a two-part answer to the question. Hopefully that wasn't too long.
As an attorney, we always try to break it down to be, one question, one answer, but I understand as a scientist, it is a two-part answer.
Yeah.
Talk a little bit, Drew, about climate change, if you would. What do you see is this a short-term impact, a long-term impact? What's the relation? Lots of questions from people on that.
Right. Well, so let me go back in terms of climate change. The long-term signal that's very clear for us in the Great Lakes is wetter and warmer. Nearly every leading climate scientist in the Great Lakes Basin, some of whom stand out, who this audience probably know about, Mike Notaro at the University of Wisconsin-Madison, I would argue is probably the leading climate scientist for the Great Lakes right now in terms of running climate models. And nearly every model he's published over the past 5 years suggests more precipitation, higher long-term average temperatures. So that's a take-home message right there in terms of climate change. However, what we've been looking at more closely is the amount of variability over shorter time periods. And what we think we're expecting to see is, while we see a pronounced increase in precipitation over time, we're expecting to see more variability in evaporation. And I'll pause there because that's the biggest take-home message I can think of when it comes to water levels and the water balance. That's the key message when it comes to climate change in the Great Lakes.
Drew, a number of questions, just practical implications here. So what does a 1 foot change in water level mean to the shoreline, for example, along Chicago? What is the impact of rising water levels when it comes to the built infrastructure along the Chicago shoreline, Northwest Indiana, western side of Michigan? Is there anything we can do about it?
Yeah, what a great question. Well, of course, the 1 foot of rise depends upon what the starting point is, but I'm guessing that the question means probably more what happens if we have, additional foot of water levels above and beyond what we might expect as a typical high. I would argue that most of the infrastructure that I'm aware of that's been designed in the urban environment has been designed to withstand a historical range, whether it be low water levels or high water levels. So an example of high water levels are sort of bridges or roads. Lakeshore Drive is a great example. The bike path along Lakeshore Drive in Chicago is another example of infrastructure that might have been designed to withstand a certain limit, a certain high and a low of water levels, but may not be able to withstand water levels that are higher. I think there's a lot of additional infrastructure in cities like Chicago and elsewhere that are not at this point designed to withstand water levels that might be, say, a half a foot or a foot above the record highs that we've experienced. And I want to mention one other part of that. Chicago is along a coastline, and there are two aspects of hydrology and climate change that I want to mention. One, especially when it comes to the infrastructure, one has to do with the water levels along the coastline and on the lake. But there's also the water that comes from inland flooding. And a lot of the discussions we are having as a research community have to do with the extent to which that infrastructure is not designed to withstand higher water levels from the lake, but also increased flooding and precipitation coming from the watershed. And they tend to meet at places like Chicago, Cleveland, Detroit, ultimately where the infrastructure isn't designed to handle that much water.
Drew, everybody may be interested. The Environmental Law and Policy Center is going to be coming out with a report and analysis in early June, talking about what is the impact of more extreme water levels on the shoreline built infrastructure in eastern Wisconsin along Lake Michigan, Illinois, and the Chicago area, Northwest Indiana, and the western shore of Michigan. The point being exactly what you just said: wastewater treatment facilities near Sheboygan, combined disposal facilities on the southeast side of Chicago, industrial facilities in Northwest Indiana, and residential multifamily housing in Rogers Park in Chicago and in the South Shore area, built right on the lake. And they were built under the conditions you're describing. they were built on the assumption that the water levels would be historic rather than how they're changing now. So stay tuned, folks. Early June, ELPC shoreline threats report coming out. And I think you'll find the modeling and the impacts on that to be really interesting, especially in light of all the questions popping up in the chat box. So stay tuned on that front. Drew, couple of questions about, you've talked mostly about Lake Superior, Lake Michigan, Lake Huron. How about Lake Erie and Lake Ontario? What are we looking at there? You had the slide about Lake Ontario with the push to Governor Cuomo, the Montreal flooding, but talk a little bit more about Lake Erie and Lake Ontario.
Sure. I do have a couple of slides pulled up. Let me pull up Lake Erie here for you. And I'll just show a slide here as a basis for discussion. So can you see this Lake Erie forecast, Howard?
Yes, we can.
Yeah. Okay.
Colorful slide.
Yeah, right. Yeah. So this is the same. I really
Drew,
like
you do good slides. Let's face it. You do good slides.
Thanks, Howard. This one I have to give credit for. We collaborated a lot with the Army Corps of Engineers on forecasting and outlooks, but I must give credit to the Army Corps for coming up with this seasonal outlook format for showing projections. I really like what they've done here. So this is the Lake Erie projection. And just as a basic answer to the question about what's happening on Lake Erie, we can see that, for the next year or so, if you look at that gray band again, going out into the future, water levels are almost certainly likely to stay above average on Lake Erie. We can see the most likely range over the next several months here. Not expected to get near record highs though as well. So really expected to stay in this band. That's sort of the short story on Lake Erie. When it comes to Lake Ontario, I'm sure most of the audience knows this, but it's worth reminding everybody that the outflow from Lake Ontario is controlled, it's regulated, primarily by the operation of a dam, the Moses Saunders Dam, downstream from the outlet of the lake. And in terms of Great Lakes water levels, it's fair to say that Lake Ontario, I would argue, is highly regulated. If you look at long-term water levels, in fact, I may do that for folks while I'm getting set up here, just to provide some context. If I can do this really quickly. Long-term water levels on Lake Ontario, if we look at this slide right here, again, of the long-term water level record, you can see all the lakes going up and down, up and down. But if we look at Lake Ontario, you can see the blue dots going up and down. And then right here in the mid-1960s, if you squint, you can see a dampening of the interannual variability. And that's due to the construction of the Moses Saunders Dam and the regulation of outflows. So why am I mentioning this? I'm mentioning this because it is extremely difficult to make long-term forecasts of Lake Ontario water levels, because on short-term timescales, the regulation, the IJC, can let water out or hold water levels in depending on navigation concerns, depending on the amount of ice in the channel, even depending on how much snow and ice is on the Ottawa River watershed that might drain into Montreal and exacerbate downstream flooding. So there's a very complicated range of conditions that need to be accounted for before water is either contained or let out of Lake Ontario. And for that reason, it's very hard to make sort of long-term forecasts on Lake Ontario. One final point I'll make about Lake Ontario, though, is that it's at the downstream end. And when there's abundant water in the Great Lakes, like there was in 2017 and 2019, it all flows down into Lake Ontario. And if you look at my hand, if you can see it right here, see those two blue dots right there, boom, right there and there. Those represent, you can see high periods. Interestingly, those were record high water levels, all-time record highs for Lake Ontario, despite the fact that it's in a period of regulation. So just the point there is to underscore how Lake Ontario is at the downstream receiving end and tends to be an aggregator of what we're seeing across the entire Great Lakes watershed.
Hey, Drew, a couple of questions that maybe you and I can tag team in addressing. First, a number of questions from people about what Drew and you and I just talk about, and we sort of know off the back of our hand. What's the flow of water through the Great Lakes? The highest lake is Lake Superior. From Lake Superior, the water flows to the east, essentially through the Sioux. It gets to the Straits of Mackinac, at which point it divides. Some goes into Lake Michigan, some goes into Lake Huron. From Lake Huron, it goes into Lake Erie, then Lake Ontario. So for folks who are asking, where does the water flow? Terrific. I knew you had a slide, Drew. This is really helpful, and it just shows you the flow of the water, but there are various points at which the water is controlled. It's controlled by the St. Mary River, by the Soo Locks. It's controlled, as Drew was talking about, to Lake Ontario and the dams before it goes to the St. Lawrence Seaway. So how those controls operate affect how much water is in which of the lakes. Anything, Drew, you want to add to that? Because we have a bunch of questions on that point.
Nope, you nailed it, Howard. While we're taking, I might pull up a top-down view, but we can go on with another question if you'd like.
All right, a couple of questions, Drew, about ice cover. More ice on the lakes. What's the impact on Great Lakes water levels?
Yeah, this one, it'll be really fun to show a lot of data and slides, but I'll sort of talk through this. The research that we have done, and the research that a lot of really great collaborators have done, suggests a very complex seasonal cycling between temperature, ice cover, and evaporation. So let me give you a quick example here. A lot of why the lakes start forming ice in the wintertime is, of course, because they get very, very cold, and that has to do with the heat that they lose in the fall due to evaporation. A lot of folks say that, oh, evaporation in a particular year might be low because the ice is capping evaporation. But I'd like to point out that that's not quite as accurate as it might sound. Let me put things a different way. If you have a very high ice year, where the ice is very, very thick in February, March, and April, maybe even in some lakes into May, what happens is that a lot of the energy that would normally go into heating up the lake in the spring and the summer instead goes into melting the ice. And so what we found is that when a lot of the solar energy that would go into the lake ends up melting ice rather than heating up the water, leads to cooler water levels in the following fall. And as I talked about earlier, if you have cooler water levels in a particular fall, you're likely to have below average evaporation. So there's a very interesting sort of feedback in terms of having high ice in a particular winter and potentially lower evaporation because of the balance of heat and energy in a given lake. So the short answer is it's a very complex cycle, but it's not quite as intuitive as you might think in terms of the relationship between temperature, ice cover, and evaporation from season to season.
Number of questions, Drew, about do the relatively small water diversions, for example, to Waukesha, how do they make a difference? Are there things that people can do that fundamentally affect water levels? Or is this more about adaptation and recognizing that water levels will be much more extreme and we have to deal with it and find new ways of effectively dealing with it? Well, what's your thinking on that?
Yeah, great question. So for the most part, if we look at an overall water balance of the entire Great Lakes system, and that's what I'm showing on this slide right here, on the left-hand side, we see these three bars, these vertical bars, green, blue, and pink on the left-hand side. Those represent the relative amounts of water that come into each lake from runoff, all the rivers and streams, from precipitation on the lakes themselves, that's the blue bar, and then the pink bar on the left is the amount of water lost from each lake due to evaporation. So that represents what we call, the water balance of each lake. On the right-hand side, Howard, are the big green bars that you see are the amount of water that flows out of each lake and into the next downstream lake. So that sort of answers the question somebody asked earlier about the flow of water through the system. All of those bars are drawn at the same scale. The numbers happen to be thousands of cubic meters per second, but the take home is they're all drawn to the same scale. The pink bars that you see here and here represent the amount of water that come from these relatively large diversions. But what a lot of people don't know is that the Agoki and Long Lake diversion here in Lake Superior represents water that's diverted into the Great Lakes Basin. It's around 200 cubic meters per second. And then here's the Chicago diversion. So just by squinting or looking graphically, you can see that those diversions are about an order of magnitude less than the magnitudes of water we get through precipitation, evaporation, runoff. The short answer, Howard, is that the amount of variability in precipitation and evaporation and runoff is much, much more than the variability in these diversions. And that's really what dictates long-term water levels. However, and I guess I would say from a management perspective, looking at these diversions as a way to manage water levels really isn't a long-term solution. In the near term, I think the thing we need to be looking at is making sure that our shorelines either are, especially in urban environments, hardened to the extent that they can accommodate high and low water levels, or when it comes to residential and commercial properties, that we might want to think about getting away from the shoreline. But the idea of managing water levels through diversions like these just isn't really a good long-term solution.
All right, I think we've one way or the other gone to most of the questions. Heads up, everybody, the shoreline threats report that we described ELPC is putting out June 15th. Thank you, Jill Geiger, is the release date on that report. We'll make sure that people who are on this webinar get a heads up when that report's issued. Drew, take a minute or two, just final thoughts, final comments, things you want to share with folks.
Sure. The first one is a point that I'll underscore that I mentioned earlier, which has to do with the long historical record of direct water level measurements we have on the Great Lakes. The Army Corps has an aggregation of gauges that go back to 1918, and then we have individual gauges that go back even further back to 1860. Just an extraordinary amount of good information to learn about water levels going up and down during that time period. The second point, though, has to do with looking into the future. And as I've mentioned, we can't just rely on the past as an indication of what's going to happen in the future. And we're sort of promoting this idea of plausible scenarios looking into the future. The reason we make that point is that these climate models we're looking at are not doing a great job of sort of representing long-term evaporation on the lakes or ice cover. But we can answer questions like, what happens on the Great Lakes if it becomes very, very wet and very, very warm? That's a scenario that we can represent in a model. So I would keep my eye out for studies that focus on things like a plausible scenario of a future climate and what that means for water levels. And the final point I make has to do with monitoring infrastructure. We're so lucky that we live in a part of the world and a part of the country where we have internationally coordinated observation statements, where we can stations, not statements, where we can learn about things like evaporation, precipitation, and runoff. And it's important that we keep those established and moving forward. So that's one final point I'll make, Howard, as we wrap up.
Thank you, Drew, for what you do and for joining us today. And thank you for the 230 participants on today's webinar. This issue is a priority for ELPC. We'll continue to work on how do we protect, restore the Great Lakes, which are so vital to our region, and how do we make sure that the shoreline's built environment adapts to the very major changes we're seeing in water levels, both mostly higher and sometimes lower, that fundamentally affects how we live, work, play, and do business around the Great Lakes. Please stay in touch with us at elpc.org. We'll be hosting more webinars like this in the future. Drew's slides and the other information in this webinar will be posted on Facebook. Feel free to share it with your friends. And thank you for joining us today. Thank you, Drew Gronewold. Stay safe.